Welcome, everyone. We're going to be breaking down Jensen Huang's recent keynote speech today. And if you saw it, it felt less like a simple product launch.
Oh, absolutely. It was more like a manifesto.
Exactly, a manifesto. So
Mm-hmm.
our mission here is to unpack that. We want to pull out the high-level strategy and figure out what it actually means for, well, the future of computing.
And if we're going to start anywhere, it has to be with the core idea. I mean, the sources we looked at all point to one single thesis, which is we're not just in one platform shift.
Right.
We're in two. Two huge simultaneous shifts hitting the industry at the exact same time.
Okay, so let's nail those down. The first one, it feels familiar, but the role is totally changed.
Mm-hmm.
It's that AI is now the platform itself.
Mm-hmm.
We're past basic chatbots now.
Mm.
It's about using these customized multi-model AI agents as the foundation for everything else we're building.
Precisely. And that second shift it's a complete rewrite of how we even talk to a computer. I mean, fundamentally, it's not about programming software with lines of code anymore.
Yeah.
The whole paradigm is shifting to training intelligence on GPUs. And the crucial part is when an app runs, it's not just executing code. It is generating every pixel, every single token from scratch based on context.
That just sounds like a colossal architectural undertaking. I mean, if you're reinventing the entire computing stack for a platform that you train instead of program,
Mm-hmm.
what's the dollar value on that?
It is truly staggering. The keynote laid out that this dual shift, it means modernizing about, what, $10 trillion in global computing infrastructure?
10 trillion.
And that's driving hundreds of billions in VC funding. It's forcing R&D budgets to shift across, easily $100 trillion of industry value. So the big question they had to answer was, how do you physically build the architecture for that when the AI models themselves are just growing exponentially?
Yeah, that's a good way to frame it. It sets up what they basically call the crisis narrative.
Yeah.
For 50 years, we relied on Moore's law, right? That predictable doubling of transistor.
And now it's over.
The sources make it really clear that physical ceiling is here.
It is. The new Rubin GPU. It only has a 1.6 times increase in transistors over the last one. That's the hard limit from physics. But here's the crisis part. The demand is totally, completely decoupled from that limit. The AI models themselves, they're growing 10 times every single year.
10 times. That's not a trend. That's an explosion.
It is. And it gets worse because the way we use these models, the new reasoning ones, the amount of thinking they have to do, that internal token generation is going up 5 times a year.
Yeah.
So your hardware is scaling at 1.6x.
But the workload is scaling at 10x.
No,
that's not sustainable.
It's completely impossible. The old way just doesn't work. And that's what forced them into this really extraordinary solution they called extreme code design.
Right.
Normally, you change 1, maybe 2 core chips in a new hardware generation. This time,
Yeah.
they did all 6.
All 6 at once.
All 6 core chips across the entire stack designed simultaneously. They had to. It was the only way, because you couldn't leave a single bottleneck anywhere in the system. Everything had to get better, and not just by a little bit.
And the result of all that is the Vera Rubin Platform, which, given that transistor limit, delivers these, jaw-dropping results, a 5x increase in AI inference performance.
And 3.5x in training.
So let's get into the nuts and bolts of that. How did they do it? What's the innovation in each component that solves a specific bottleneck?
Okay, let's start with the Vera CTU. It has 88 custom Olympus ARM cores. But the number of cores isn't really the story.
Next the story.
Its purpose. This CPU has been totally redesigned to be the feed mechanism. These new agentic AIs, they need constant, super fast, small bursts of data. The old CPUs couldn't feed the GPUs fast enough.
So the system was starving.
Exactly. The GPU was just sitting there waiting. This new CPU uses something called spatial multi-threading to handle 176 threads at once, just to make sure the GPUs are always saturated with data.
So the CPU's main job is no longer processing. It's just making sure the GPU never waits for dinner. Okay. But how did the Rubin GPU itself get that 5x performance lift if the transistor count only went up 1.6x? That seems like the real magic trick.
The magic is something called the MBF FP4 tensor core. They're basically shifting performance away from just, brute force transistors and into smart engineering.
Okay.
Think of it like this. Your calculator usually uses fixed precision math. It always shows you like 8 decimal places, even if you only need to.
Right, which is wasteful.
Very wasteful. The MBF FP4 is like smart math. It adjusts its precision in real time. It decides on the fly exactly how many bits of information it needs for that one calculation.
So it's not wasting energy and time on calculations that don't need to be super accurate. It just focuses its power where it's mission critical. That's a fundamentally smarter way to do it.
It is, and that's where most of that 5x gain came from. But once you solve the single chip problem, you immediately run into the next wall, the network bottleneck.
Because these huge models need dozens of chips to act like one single brain.
Precisely, and that's where the NVLink 6 switch comes in. The numbers here are just, they're stunning.
Go on.
It delivers 240 terabytes per second of bandwidth.
I don't even know what that means in the real world.
Okay, get this. It's double the data flowing through the entire global internet. All the videos, all the texts, all the websites, twice that amount moving through one tiny box in a server rack.
Wow.
And you need that. You absolutely need that to make sure 72 or even 144 GPUs can operate as one without any latency. If they can't talk fast enough, the whole system just grinds to a halt.
Speaking of grinding to a halt, let's talk power.
Right.
That's always the elephant in the room with these massive systems. I saw this claim about data center efficiency that just sounded almost too big to be true.
It's a huge claim. And it all comes down to the liquid cooling system. They moved to this high-efficiency 45 degrees Celsius warm water cooling.
Wait, 45 C? That's like 113 Fahrenheit. That's hot water.
It's hot water to us, yeah. But that temperature is the key. Because it's warm enough that you don't need those giant, power-hungry water chillers that data centers use now.
And getting rid of the chillers is the big win.
It's the whole game. By eliminating them, they claim they can save 6% of the world's total data center power.
6% of global data center power. Can you put that in perspective?
That's roughly the total residential electricity use of a whole country, like, say, New Zealand. So this isn't some minor tweak. It's a massive economic and environmental breakthrough. It just dramatically cuts the cost of running these things.
Okay, so you have this incredible hardware efficiency, but that doesn't really matter if the software demands are spiraling out of control. Which brings us to the AI models themselves, the jump from those simple parrot models to reasoning models like DeepSeek R1 that can actually strategize.
And that jump is all about a concept called test time scaling, TTC. The core idea is that getting an answer from an AI isn't a one-shot deal anymore. To solve a really complex new problem, the AI has to run thousands of internal steps. It's basically running little simulations, planning things out before it gives you the final answer. It's thinking out loud, but internally.
And all that thinking generates a ton of tokens.
A massive amount. And that's where the economic tension really becomes clear. On one hand, Vera Rubin gives you this revolutionary efficiency. It makes generating a token 10 times cheaper.
Which sounds like you've won.
It does. But if the AI needs to generate 5 times more tokens every year just to think, then where do you actually end up?
This is the central irony of the whole keynote, isn't it? It's the Jevons paradox, but for computation.
That's exactly what it is. The hardware is incredibly more efficient. But that 10x cost reduction makes intelligence so cheap that you suddenly unlock all these new energy-hungry things you could never do before.
You create the efficiency just so you can immediately consume it with bigger problems.
And we see that playing out perfectly in how they're solving the memory wall.
The KV cache bottleneck.
Right. These new agentic AIs, the ones that are supposed to manage your calendar or run your factory, they need to remember things for days or weeks. But the super fast HBM memory on the GPU is tiny. It's expensive. So the AI has short-term memory loss.
It's like a brilliant strategist who can't remember what happened yesterday.
Exactly. They forget the context. So the solution they introduced is really revolutionary. It's a component called the Bluefield-4 DPU.
So what is a DPU? What does that actually do here?
Think of it as a specialized traffic cop for memory and networking. It takes the job of managing all that context memory away from the GPU. It uses high-speed networking to create this huge shared memory pool inside the rack.
How big are we talking?
They're adding 16 terabytes of shared memory per GPU. It's a monumental increase in capacity.
So by solving the memory wall, you give the AI a true long-term memory. You enable those continuous, personalized agent workflows. But again, this just drives more demand, doesn't it?
Yeah.
Absolutely. The moment you enable 16 terabytes of context, people will build agents that use all 16 terabytes. And those agents will run for longer, demanding exponentially more compute time, which could easily overwhelm those initial 10x efficiency gains. The solution to the bottleneck becomes the engine for the next demand explosion.
Okay, let's pivot now to that second major platform shift you mentioned at the start, physical AI. This is where we take intelligence out of the screen and put it into the real world.
Cars, robots, factories.
Yeah, and that's a huge leap. The AI has to suddenly understand causality, common sense, the actual laws of physics.
And to go from generating text to, say, operating a factory floor, you need a very specific architecture. The Keynote laid out 3 separate computers, all working together.
Okay.
You need one for training the big models. You need the inference computer, the little robotics brain that runs at the edge inside the robot or the car. And then you need the third one.
The crucial one.
The crucial one. The computer that does nothing but simulation. The Omniverse digital twin. And this is the answer to the biggest problem in physical AI, which is data scarcity.
Right. How do you get billions of miles of real-world driving data?
You can't. It's impossible. Or how do you test every single failure mode on a factory assembly line? You just can't do it in the real world.
So the breakthrough is just generating synthetic data.
Exactly. You turn compute into data. And because the Omniverse simulation is grounded in the laws of physics, the data it generates is physically accurate. It makes sim-to-real possible at a massive scale. It just solves the data problem.
And we saw a couple of really fantastic concrete examples of this platform in action. First was in the car industry with a system called Alpamayo.
Right, Alpamayo. They described it as the world's first thinking, reasoning, autonomous vehicle AI. It's an end-to-end model for vision, language, and action. But the key insight, the really important part,
Is that it can explain itself.
yes. It can explain its driving decisions in real time. If the car has to swerve, it can tell you why it swerved. That is huge for solving the trust problem with self-driving cars. And it lets the AI reason about novel situations, that long tail of just weird stuff that happens on the road.
And I think it's really important to note that they're open sourcing the model and the data. They want everyone to build on this. The second big example was the industrial side, that partnership with Siemens.
That's the industrial metaverse vision. Siemens is basically embedding this entire stack, the chips, the AI, the Omniverse, right into their industrial software. It lets you design, debug, and optimize a whole factory, which is really just a gigantic robot in a physically perfect simulation before you ever pour the concrete.
The factory of the factory.
Exactly. And the potential savings in time and money for the $100 trillion industrial sector are just immense.
So the final picture from this keynote is one of complete vertical integration. They're not just selling chips anymore.
Not at all.
They're providing an open, full stack. From the silicon architecture like Vera Rubin to the simulation infrastructure like Omniverse, all the way up to the foundational models like Alpamayo and the open libraries. The message seems to be, here are all the tools. Now every company, every country can build on these 2 new platforms.
And, to tie this all back to our initial idea, this huge vertical integration, the crazy performance gains from Vera Rubin, it's all designed to make this the only path forward. The shift is basically complete. Intelligence is now customized, it's multi-model, it's agentic, and to run it, you need this new physical foundation.
And I think that leads us to the final provocative thought for you, the listener, to take away from all this. The immense power and the efficiency of the Vera Rubin platform, especially combined with that 10x token cost reduction, it completely changes the economics of intelligence. But that Jevons paradox is a real threat, a massive one. Even with a 6% data center saving, which is huge, is the planet's energy supply going to be enough to sustain the unlimited demand that this cheaper, more powerful AI has just unlocked?
It's a profound question. We are watching a societal experiment unfold right now in real time, as every physical thing from your car to a factory becomes a reasoning smart terminal powered by these huge learning AI agents. What does that mean for our position, for humanity's position, in a world that is increasingly being designed, driven, and built by these autonomous systems? It's a question of scale and speed and sustainability that, well, it demands we keep a very close watch.